So, my name is Mitsuhisa Sato from the Riken Center for the Computational Science. So, I'm Deputy Director of my centers, and also my main job currently is the team leader of architecture development team for flagship 2020 project, which to develop the Fugaku computer. So, thank you for organizers' invitation, and I'm very pleased to be here, having the opportunity to give a talk about our co-design experience. So, first of all, some of you already know that our the Fugaku system and project. So, our system is the many core system, which is using the ARM instruction set plus the SVE, scalable vector extension. So we have no accelerators, and so that I'm going to explain the latest detail about our architectures. So as a result of the co-design the effort. So before talking to the co-design process, I'd like to present some update of our project. So the Fugaku system is so-called POST-K. Is the flagship machine following the K computer. So K computer in August, K computer is decommissioned, and we remove the computer from the computer room because the new machine, Fugaku, will be installed in the same the computer room. So, and last month, so finally we got access to the test chips, and after I'm going to present the recent early result from test chip. So, and at last week, we have the SC conference in Denver. So at the conference, Fujitsu is announced their product, FX1000. That is the commercialized version of the Fugaku, and also the cluster version of Fugaku system. That is the air-cooled, and connection, interconnection is by the InfiniBand. So, and they announced a collaboration with business collaboration with Cray. So we are very happy with that. So because one of the problem at the K computer is that K computer is not sold in the outside of Japan. So this time the Fujitsu will have the business in the outside Japan. So and finally we fixed the frequency of our system. So 2.0 and boosted to the 2.2. So that means that our system is going to be the half exaflops machine. In a peak performance. So with a general purpose processor. So and finally at the SC, we are happy with the prototype system to rack got a #1 position of the Green 500. So here, so this is the copy of Fujitsu announcement. So the clock frequency near to the 2.0 and 2 racks, and power efficiency is 16.9 gigaflops per watt. This number is very impressive, and we're happy with that. So the number is coming from the general purpose processors, not the accelerators like GPU. So, and from next month, we start the installation. So installation takes 5 or 6 months, and because of the large system, and we have the system at least the summer of the next year, and after testing and acceptance test, we are going to start the public service from spring or summer of 2021. That is the update of our project. So, okay, let me talk about what we did for the co-design for the Fugaku system for Sato. So at the beginning of the project, so we decide the 3 the KPI, key performance indicator. So one is the power efficiency. So we fixed the power capacity of our facilities to the 30 to the 40 megawatt. So, and next one is we much care about the efficiency of the real application. So, and we expect the 100 times faster than the K computer in some application. So K computer is the 10 petaflops machine. So it's the 100 times means that the exaflops, but this is a kind of the definition of our exascale, extreme scale, the computer. And last one is that easy of use system. So this the facilities is shared by the all over Japan. Of course, you can apply to use this system. So that is the third items for the KPI. So finally, for the power efficiency, the last year we confirmed the 50 gigaflops per watt in test chip, and now we got the first position of the Grid 500. So, next one is that we confirm the 125 times faster than in MD application, and also 100 times faster than in the climate simulation and data simulation the program. And last one is that our system is just main core system without GPU, so the user don't have to pay any effort for the programming for the accelerators. And this is kind of the demand from the users from when we started the project. So this is the target application. So I'm going to talk explain the later. So this application, and in this application, we confirm 100 times faster than K computer using the capacity of our electric capacity of the 30 to the 40 megawatt in a system. So, okay, let me talk about the co-design, especially for the HPC. So if you take a look at the co-design in a Wikipedia, so this statement is found in a web page. So I think co-design is a process of the software and the hardware. And also this page says that the co-design is mainly coming from the embedded system, like a mobile phone. So I think the co-design of the HPC is a little bit different. So they're different from the embedded system because we are designing the large-scale system, which is shared by everyone. That means that the co-design is not just for the kind of the specialization, but also we have to exploit the maximum the performance for a set of the application. So that is the different from the co-design of the embedded system. So, and why we need a co-design process in a very high-end system? Maybe everybody agree with that. So we need a design for the system to trade off between energy and power and the cost. So to satisfy the constraint on the energy, the power, and so we have to build a system within our budget. So and at the same time we have to maximize the performance. So that is why we need the co-design. So that means that taking a look at the characteristics of the application and design the system. So, and the co-design of our post-K project is different from university project. So, University Computer Center is picking up the processes and picking up the interconnect and do the design by the combination of the existing component. But in our project, we design the processors itself. So that is the big difference. Okay, so co-design is the bidirectional the effort. So that means that from the application to the architectures and the circuit the design. So and analysis application to drive the most efficient solution. This is the direction of the down the direction, and at the same time we need another direction. So if we fix the architectures, we have to tune the software to get the maximum performance of hardware. So first, I'm going to talk this direction. So let me talk about what we did in before starting the flagship 2020 project. So the K-Computer project is that from 2006, so 2006 to the 12. So public service of the K-Computer is started from the 2012. So at the moment of the K-Computer operation started, we started the feasibility study project from 2012 to the 2013. So one application feasibility study and three the project for architectures. The one is the University of Tokyo. They are exploited in a general purpose supercomputer and with the collaboration of Fujitsu and me at the University of Tsukuba. So we are doing the research for the exascale heterogeneous system by the accelerators. And Tohoku University is there exploited the vector type of the computer. So, and the project is started from 2014, and at the time of at the beginning, so initial plan was the combination of the general purpose supercomputer and the accelerators. That is the combination of feasibility study of the University of Tokyo and the feasibility study of the University of Tsukuba. But unfortunately, at the very, very beginning of the project, the accelerators was canceled due to the budget problem. So finally, basic design is that follows the general purpose processors, which is conducted by the University of Tokyo. So, and project is started from the 2014, and almost co-design was done in this phase. So from 2014 to the 2016, 3 years. So after the 2017-8, that is the more detailed design and implementation. So this is the list of technologies of the architecture parameters to be determined by the co-design process. So for the chip configuration, we have to decide the number of the cores and the number of NUMA nodes, and also what kind of the configuration we should take, and chip connection, and the memory technologies, including HMC and HBM. And of course, the frequency and what kind of silicon technology we can use. That is a very important factors for co-design. And also, within a core, how many pipers, how many vector rings, and also cache and out of the resources, and what kind is any the specialized hardware or something like that. So the difficult point is that we had to examine these kind of technologies available after 3 or 4 years from the co-design. So here, technology trend is aligned to our project. So silicon technologies and memory technologies and network technologies and I/O technologies. So at the moment of co-design process, so we have to choose what kind of technologies we are going to use when we are making we make the real chip. So the silicon technology at the moment of co-design process, 16 nanometer FinFET technologies, but we are expecting 7 nanometer FinFET technology will be available at the time of the manufacturing. That means that 2019. And also, the difficult point is the memory technologies. At the time of the co-design the phase, so HMC, the high memory, the hybrid the memory cube technology is available. But you know, the Micron is canceled these technologies. So we have to switch to the HBM. So, and we expect HBM2 will be available at the time of 2019. And silicon interposer technologies and network technologies. So I think very the unfortunate is that PCI Express. So post-gate chip is still have the PCI Express Gen 3 by 16, but little bit later, maybe you can use the PCI Express Gen 4, but we cannot choose the PCI Express Gen 4. So, and the chip configuration is a very important the design factor. So, and that means that, so here, is any pointers? Okay. So this is the, I show the example of chip configuration at the below, is the 4 patterns, but there is many patterns. So, for example, small chip and HMC and connected by the network, and large chips and using the HMC, and also small chip, which is mounted on the multi-chip module, and which is connected by the inside chip, like chiplet technologies, which is getting popular in now, or the large chip and HBM, and this is the final selection we choose, final configuration we choose. So to choose these kind of factors, cost is very important. So this is the the relationship, the cost, and chip size. So up to the certain amount of the area, so chip size, chip cost is proportional to the chip size. But beyond some point, so the cost is getting higher. So that means that to decrease the cost, we keep the chip smaller as possible, at least less than the certain amount, the size area. So that is very important factors to decide these configuration. So, and how to decide? So to decide this kind of the configuration, of course, the cost is very important. At the same time, the performance is also important. So performance was estimated by a kind of the analytics model of a simple kernel like HPL. So, and the target application. So we have, our project is not just only the development or building the system, but also development of the application which is running on the Fugaku machine. So at the beginning of the project, government is identified 9 priority issues from listed here, and each the issues our project is selected and organize the project to design the application to solve the problem in this area. So, and we asked each project to submit the one representative application. These are lists and from MD and so, and also we picked a typical benchmark such as the HPL and the stream. So, and for the target application, it's not just only the representative of the application, but also it will cover a kind of the computational the patterns or communication patterns to design the system. So, and tools for co-design. We first use the performance estimation tools. That is tools enabled the performance projection by using the Fujitsu the FX100 the execution profile. So the application first we run the application FX100 and take the very detailed profile, and Fujitsu provide us to tools to the projection to the new architectures. So this is modeled by the Fujitsu microarchitectures. And also Fujitsu has in-house simulators. It's not for open for us, but first they have the Spark simulators. This is the FX100 the simulators, and also compiler for this. So we are using this the simulators as a preliminary studies to decide how much vector length we need and how much the cores and how much the computing resources out of the resources we should have. So, and after that, so they developed the V8 and SV simulators using the same simulators. And Riken designed the Gen 5 simulators, but this is not for design. This is for the architecture verification in our side, and also the performance tuning by the Riken. And the last one is the emulators. So emulators for logic verification. So this is the performance estimation tools. So sorry for Japanese. So we only have the Japanese. So, and this tools is the display like this. So, and this is the parameters. So memory busy time and the memory the write busy time and L1 busy time and L2 busy time. So combining these profile parameters, this tool is generate breakdown of the execution time like this here. So this is reflecting the microarchitecture of the Fujitsu. And then by putting the new parameters of new architectures, so if we increase the memory bandwidth, then memory busy time is getting short and something like that. So this is by the projection, by the throughput of each element. So this approach is very similar to the roofline model. So and this tools can generate the performance of the execution time of new architecture parameter. So, and using this, we did co-design like this. So first setting the system parameters and tuning the application, the system parameters, then the evaluation using estimation tools, and identify the hardware bottleneck in changing the set of the system parameters. We repeat this process for the co-design. And also, we are using the analytical model for simple kernels such as HPL. So, and for this, first we identify the kernel loop. Taking the target application, we extract some kernel loop like this, and generating a profile, and using the estimation tools. Each profile is generating the execution time of this kernel. And from execution time from each the kernel, we can calculate the total execution time. And after that, we extract this kernel, and set of the kernel is used for evaluating the performance of the simulator also. So this is the one of the process we did in a co-design. And this is the optimization for FX, the A64FX processors. So these processors have a kind of optimization for gather instruction. So if the gather the access is within the set of the cache line, then the requests can be combined. This optimization is one of the results for the co-design process. And also, we care about in the power management and low power design. Of course, the low power is coming from the using the leading edge technologies of the 7-nanometer technologies and low power logic design. But also, we designed a lot of the controlling of the element. So, for example, we have the two pipe of the floating point. We can switch off by one pipe, or we can change the frequency. We call these kind of parameters power node. So, and echo mode. So we switched off the one pipe, then we can not only using only one pipe, but also we can reduce the standby power for the arithmetic unit. So this is the much the contribution for reducing the power. So that means I'd like to note that. So 4 applications out of 9 target applications, select this echo mode for the maximum performance under the limitation of our capacities. That is even using the HBM2. So that means the floating point performance is enough just using the one pipe. Two pipe is too much. So that is I think this kind of mode is very useful to reduce the power. And the co-design for the network is that we have selected top network because we need some compatibilities for the K computer in a large-scale application. And we select 28 gigabit per second line technologies available around the 2090s. And almost the performance evaluation is done by analytical model. So communication patterns were extracted, and the performance is estimated by the analytical model. So, and according to this co-design process, many applications just enough for neighbor application or point-to-point application, but some application must have auto communication. So we studied and feasibility of the additional dedicated the all-to-all network, but it's not selected by the cost. But we support 3 double precision the reduction supported by the TOF network. So that is for the speed up of the QCD application. Okay, this is the result. So this is a chip figure, and here are the chip and HBM2. HBM2 is mounted on the same silicon die, and which is connected by the coarse technologies by the TSMC. So, and these cores, so, and here, 12 core, actually 13 core is a NUMA node, or sorry. So, and the core is sharing the L2 cache. And this NUMA node is connected by the on-chip network. And upper side, you can see the network interface. And side is the HBM2 the interface. So, and this is the specification. So, and the normal the frequency is 2.0, and the boost frequency is 2.2. Okay, so, and so TOF interconnect is like this. So we have TNI is the TOF network interface. This is the DMA engine from memory to the network. So, and we increased the 6 the DMA engine from the K computer, which have the 4 the DMA engine. So this is the first result of the performance of the network. So the throughput is improved from the K computer, and the latency is also improved from the K computer, like this. And then, okay, and the prototype, 2 chips is mounted on one board. So, but it's not shared memory. So, and the rack is has the 384 CPUs. It's very dense. Okay. So, and this is the system configuration, and that we are going to have 150K nodes, and by this number, using the boost mode, this system is going to be half exaflops machine. And the three hierarchical the storage system. One layer is the SSD, and this is used for temporary the storage, and also in the cache of the global file system. And the global file system is designed by the Fujitsu and based on the raster. And the third raster system. And the third one is the cloud the services. So I will skip this. Okay, the co-design HPC is now the another direction. So from hardware to the software. So at a very early stage, before the coming of the chip, so we are doing using the performance estimation tools, and also the Gen 5 simulators. We are testing, we are evaluating the performance. But now we have the test chips available. Currently, we are tuning the performance using the test chip. So let me talk about the performance result. The Cloverleaf and T-Leaf is coming from the UK Miniap, and the Willish is coming from the Lawrence Livermore National Laboratory. And we compare the A64 test chips and also SunX2 and the Broadwell and the Skylake Intel chip. So, and this is the result of one CMG, one NUMA node without MPI. So we found that a good scalability by increasing the number of threads within CMG. So please note that one CMG performance is very comparable to the one Intel chip. That means that we have the 4 CMG within the chip. So this is a very good number. And this is the evaluation of MPI program, the one chips and using the one the MPI process. So and we have the twice the performance compared to the Xeon process dual socket processors, dual socket node. But we found some the memory limitation from more than 4 threads. And the Willish is that this is not so good. So the result, so that is because of the we found that the low vectorization. So we checked the performance profile, and then we found that the SIMD instruction ratio is just a few percent. So to tune the performance of this kind of application, we need we need a tuning to make use of the SVE. So this is the slide of from the Fujitsu, so I will like skip this. So okay, concluding remarks. So we are happy with the co-design. So we achieved in 3 KPIs, and the power efficiency and effective performance of the application and ease of use. And we are very proud of the very well-balanced system of the server application. But at the last message, dark side of the co-design process, especially for the HPC. So co-design is a good process, taking a look at the application and design the system. But for the HPC, we have to maximize the set of the application, different application. In that case, it's not so easy to use the destructive architectures like accelerators. So at the beginning, at the very, very beginning, that we choose we have a design, we are thinking a design of a combination of accelerators and the general purpose CPU. But this accelerator is canceled, was canceled. That's because of the budget problem. But also it's rejected by the many the application users. Application users don't want to use the new accelerator. So I'd like to point out this dark side. And also, but I think in the future, to exploit more power efficiency in the future system, we need some application-specific accelerators for some system. But this is the kind of conflict to the co-design process of the HPC. That means that accelerators, GPU is almost good for many applications, but anyway, to increase the performance, we need more and more application specific, but that means that it's not easy to use by, not easy to share by the many users. So okay, that is my talk. Thank you for attention.
Thank you very much. Des questions? Open for discussion, questions? Il y a quelqu'un? Pas de... Tu veux m'aider?
Thank you very much for your talk. I'm Isabelle Persay from INSOM, the French NIH, and I would like you to elaborate on the applications. So I noticed that the two first applications were in the medical domain, drug discovery and genomic. What are the applications that better scaled, and what were in detail, what were the speed up? Because application by application, you didn't give the numbers, and I would be very interested by this.
Yeah, so application speed up. Okay. So this is a result of the speed up of our application, the target application. So this is I think first these two is the MD and the genome is a sequence matching application, and roughly saying the many application is can be speed up by 40 to the 50 times faster. But genome is limited to the 8 times. That means that this application need more memory, file access, and it's not easy because it's a combination of the very, very general purpose combination, as a combination of set of the general purpose application. So it's not good for, not easy to use for the speed up in this system. But I think at the time of the K computer, many people is interested in a kind of capability computing. So what we can do for using that large scale system. But now for this system, many people is interested in a kind of the capacity application, capacity type of application. The running the many cases and by using this computing resources. So that means we are going to provide a kind of the cloud and container type of the solution for this system to run the many general purpose application. Yes.
Is the code available somewhere?
Yes.
The code is in free access?
Yes.
Okay.
Edouard? Attends.
Thank you. Can you, so you mentioned performance speed up for this application, but for many developers, an important point is how much effort was needed to reach this performance. And you said you had not a very disruptive design, but a design of the machine which was easy of use. So could you comment of the effort that had to be made by developer to reach this performance level?
So I think this is a good result. The result for the general purpose application. So we can observe the up to the 1 point times faster than the Xeon recent Xeon processors, the socket processors. So this is just comparing to run, because you can use the OpenMP hybrid program. So you don't have to do any things about the accelerators.
So that you mean that there was no need to modify the applications?
I think so.
The applications were mainly ready with OpenMP and could benefit
Yes.
from the technology? And compared to your previous table, why there are two applications that can reach the factor 100? It's what is specific to those, or why is it more adapted to those? Do you have a comment on this? Or it's too difficult to say?
So MD application is that application is the capacity application. So and so one MD simulation is run within a one node. So and that means that so it's easy to parallelize, and also we are thinking the bytecode design process. We are using the half precision calculation to speed up. And also for the weather, climate, the data simulation project, we tuned a lot of system software to communicate between, to exchange the data simulation to the data simulation.
Okay. Thank you very much. I think we can thank you again for your very clear presentation and impressive results.